new phases. Last year we sat in your seats, starting with the master, which was then still called electrical power engineering. Now I think it's something electrical stability energy. But that doesn't mean we're still we're the student board of our master program, the SSD, sterkstroomdispuut. It means something like power, current, something. No. So this is called SSD. So my name is Reinhard Gethoyer, and you can call me Ray. It's easier, I guess. And this is Isabel and Wim, and we are on board. And we have a lot of events, organized by us and for you. So last year, for example, we went to Berlin for 4 days for a very, very low price. So we have a lot of nice events you really want to join. And that's why we're here, to make sure that you know that we exist and to make sure that you are following the events. And the first event that I want to mention is next week, after this lecture actually, so we'll be here to pick you up and take you. There will be a drink in the Slash Pub. Do you know what the Slash Pub is? Okay, well, it's a bar over here. It's a drink from the SSD, free drinks, yes. So whatever beer or whatever you drink, it's free. And you'll meet all the people from last year and from the staff of our master program. So be sure to be there. We'll drag you in. You're standing out here and we'll drag you in, so don't worry about that. And there are 2 other events actually coming up. There is probably coming a trip to Venice. I'm not sure, you probably know what Venice is. And we're going there to Alstom to see some nice factory over there. And there is on 21st
of October is the symposium. It will be about smart grids. We're very busy organizing it right now, but you'll hear of it later.
Yes, but there will be a lot of companies there who are looking for employees and stuff. So be sure to be there to make sure that you maximize your job opportunity. So that's it for now. And if it's okay with you, we want to send around a paper with. You can put your name on here and your email address, and then we'll mail you just a few times, but just to make sure that you don't miss the free drinks and the trips to, I don't know, Venice or Berlin and the symposium. Is that okay? And you can then take a free pen. So please don't make sure to. Yeah, just keep it. And thank you for your time. Good. So see you then next week. And you can come too if you want. Thank you.
21st.
I can use a drink after giving electrical. No, I don't. No, but I already mentioned them, I think, last week, or at least to some of the students. I fully support everything. For instance, one of the things, so if they organize excursionists to see a real power transformer from nearby, and so you're the power transformer I'm looking at too, which is really impressive. It's not just something old-fashioned; it's really high-tech. And normally you would never have that opportunity or anything else, and it's nice.
It's a good point.
But can you imagine about some 30 years ago? I was like them. I was also in the SSD, so it's really nice to become involved also with your fellow students. So I know that many people from abroad, they're here to pay a lot to study here. So you focus 100% on things like this here. But part of the education is really going with these girls and guys. Not drinking. It was you. No, but honestly, it's very valuable. And you get in touch with maybe your future employer. That's enough.
Good. Thank you. Oh yeah, of course. Please use it.
Thank you.
You're pushing.
Okay, I will use this pen to write down your mark after the oral exam. Okay. Okay. Thanks.
Thank you very much. And good luck.
Sorry. There's no. Well, you can sit there, but please take this another one. Because I can't come here. Quit? No, why? Maybe we have an extra chair in G.
You can take
Oh, here's, I don't have to shift. That's the luxury problem, this. Okay. Focusing our attention to high voltage again. Now, maybe some of you have seen this this thing here. It's here on purpose because I expect you to know what it is after last week's meeting. Okay, let's do it like this. Those of you who think they know what it is, please raise your hand. You're not in danger. So one careful hand there. Only one. Two. Okay, these two guys get 3 bonus points. The other ones get 3 minus points. Because what is this? There's a picture in the handout. It looks slightly different. At least the minimum you could say it looks strange, yeah? Do you think you can find it somewhere in our grid? Do you think I took it out of my kitchen as Armando thought? It's like what industrial mixing machine? Oh, no, I'm teasing you. No, this is the inner part of a traveling wave tube. Yeah. Does that ring a bell now? TWT still doesn't ring a bell. Okay. I know I joke a lot, but some of the things I say do make sense. This is the ultra wideband amplifier that is used in satellites. Yeah. It amplifies a signal, let's say 6 decades, without adding any noise to it. And you need high voltage for that because there's an electron, this is vacuum inside, this vacuum tube, and we have a cathode and an anode, so electrons are accelerated through this tube, and in some magic way, the energy in the electron beam is partially transferred to the microwave signal that goes around, and we get amplification. So, and we need high voltage for that. These things you can find in all the satellites. Or if these things wouldn't operate, we would have no communication whatsoever. Interesting, huh? At least I think it's interesting. They still use classic technology. Why not use solid state technology, power electronics, and so on? Does it have the same reliability? It's very simple as that. Because reliability is an issue in high voltage engineering. Our equipment needs to live for how long was it? 30, 40 years. Yeah. These things, they need to live, let's say, for at least for 15 years, and there's no possibility for any maintenance. Continuous operation, 15 years in space. So there's a lot of challenges there in designing these things and making sure they live so long. Okay. So I tried to bring something with me that reminds you of should remind you of last meeting. Sometimes in words, sometimes in real. Okay, where did we? What do you think was one of the most important messages last time? Then the message comes. But honestly, what do you think was one of the most important messages last time?
Electric field.
Yeah, you say electric field, yeah. Well, what about electric field?
Strength of the electric field.
It's all about the electric field. If I interpret your words, all about the electric field. It's not so much about high voltage. It's the electric field. It's how much we stress electrically the dielectric means later. We'll come to learn much more about it. So I look a bit at a strange screen here. Forgive me if I go very fast through this. Wait, this one. That should have been the link. I know, it doesn't look exactly the same, but okay. Yeah. So, to the right, that's in the house. The travel wave tube. Okay, we did all small dash. We spoke about the three operators, remember? Yeah. And we ended here, equipotential lines and field lines. Remember, there's no exception to the rule that they have to be perpendicular always, and field lines are always perpendicular to the electrode. So because an electrode is an equipotential surface. Okay, now let us have a look at. I guess this is the simplest object. This is a parallel plate capacitor. And if I would say to you, okay, if we apply a voltage V across, and we have a surface area A of the plates, and the distance between the plates D, and I ask you, what is the capacitance? What is the electric field? What is the capacitance? You would not hesitate in giving me an answer to that question, right? What is the electric field? Distance D, voltage V. It's V divided by D, but what? Take the thing as it is drawn there, this size and all this plate. Yeah, you have edge effect. Yeah. So in fact, when you say the electric field is voltage divided by the distance between the plates, you really assume the plates are infinitely long. Yeah. Or taking the real physical thing, you can say, okay, this is true only in the center, the capacitor, and the closer I get to the edges, the further away I get from this V divided by D. This is important to realize. Okay, but you know that the field is V divided by D because you've memorized that or somebody told you. But how can you calculate that? How to calculate the electric field? You do that by using Maxwell's equations. These are the tools that you have available. Yeah. And I will guide you through one calculation just to show you how you do that. Of course, then if you know that, you can take on more complex situations. So we have a few assumptions here. The first one is, for now, the plates are infinitely long. The second one is, the potential on the first plate is U, on the other plate is 0, it's grounded. And then to be very general, we assume that between the plates there can be charge, free charge. Remember that we need to use Poisson's equation, remember last time? It's a general equation. So that we assume a certain charge density, rho, which can be dependent on x, y, and z if we are in a Cartesian coordinate system. And we say that is rho. So it's constant, in fact. I don't want to overcomplicate things. So we have a constant charge density between the plates. Then, so on top there, on the right top corner, that's the situation. Yeah? You have to make a proper sketch of the situation, also direction of x, because we're working with electric fields which have a direction. Yeah? So, evidently, because there's a charge density, we have to use Poisson's equation. And Poisson's equation in how many dimensions? We want to make the thing as simple as possible. Only in one dimension, yeah, because we assume the plates are infinitely wide. So we get d square u dx square equals minus rho divided by epsilon. And epsilon is the permittivity of the medium between the plates. Okay, and now it's rather straightforward. Now we integrate the electric field from one plate to the other. And if you take one single integration, then you get du dx, right? Yeah? Equals then minus rho divided by epsilon times x plus a constant 1. Or if you turn it around, the electric field equals minus du dx equals rho divided by epsilon times x minus c1. That's the first step. But there's still this constant. But we can integrate again, and then we get the potential distribution, Ux. And then we see that we get a relation with two constants. How to get rid of the constants? Well, we know the boundary conditions. So we know that the potential at x is 0 is 0. So that gives you C2, 0. We know that the potential at x is d, at the other plate, should be u. So we get for C1, the constant C1, the value as you see there, u divided by d plus half times rho divided by epsilon d. And now we have it on the left below, we have an expression for the potential between the plates. Yeah? That's not what we set out for. We want to know the electric field between the plates. And the electric field was, we just fill in, we have the top relation there, we now know C1. So this is the expression for the electric field. Of course, when you make such an exercise, you should always do some checks. For instance, if there's no charge between the plates, then the field should just be u divided by d. Yeah, that is one check. It's the easiest check you can do. And you see now that the electric field is a function of x. So it's no longer constant, but it's increasing. If you would plot that, simple Excel plots here. See here's the potential and the electric field to the right, plotted as a function of x. You see the electric field goal is really negative here, the way we chose the directions. But we have a linear increase of the electric field between the two plates. So this is the way to do it if you use the differential equations like Poisson's equation or Laplace equation. Okay. And you see that in this way you could have also calculated the electric field in a parallel plate capacitor without space charge in a proper way. And then just take rho 0. It sounds strange, I guess, to some of you that we all know that the field parallel plate capacitor is u divided by d. So why calculate it? But you shouldn't assume too much. You always go to the basics. You will notice that those of you who took exam with me in other courses, and know I want you to understand this. Not just say, oh, everybody says it's u divided by d, or when the book says, no, I'm going to ask you about why. Yeah. Okay. Then I'll remind you of some stuff you got also in your bachelor, I assume, I hope. These are the boundary conditions for the electric field. So what happens if we go from one medium to the other? For instance, from oil into paper, from air into epoxy resin, between two dielectric media. So suppose you so this is the interface between two media, medium 1 and medium 2. And our media are characterized, in this case, only by permittivity, relative permittivity. So this is epsilon R1 and epsilon R2. That's the only thing we have to worry about. Now suppose we know, for some reason, that medium 1, this is the direction of the electric field, and this is the magnitude of the vector. Now, maybe you can understand that it's of some interest to understand what happens to the electric field in the other medium. And this is where you need to use the knowledge about the boundary, what happens at boundaries with the electric field. Now you should know. I'm not going to deduce it. You can figure it out by looking again at all at the handouts, but it's basic stuff. What you do, so this is E1. You decompose it in two parts. One part is perpendicular to the interface, normal to the interfaces, and one part is parallel to the interface, or tangential, so don't mix up the two, please. And if we stay very close to the interface, but this is a situation in material 1. Now we look at the other side of the interface, but infinitely close to see what happens. Then we know that the tangential values do not change. So I write them here as vectors like this. That doesn't change. For the normal component, it's in the next slide. Something changes. But the precise condition is given for the dielectric flux density, which is D. But you all should know that's a very simple relationship, in our case, between D and E. For the normal components, we get D normal 1 equals D normal 2, but only if there is no free charge on this interface. But as I said already last time, we assume we have no free charges. You have to visit me at the other series of lectures in high voltage DC, then we deal with free charges. Here, we may assume that there are no charges. And then we can make this simple statement. We move to electric fields. And how do we move to electric fields? This one is epsilon or meaning 1 times and 1 equals. Yeah, okay. Or let's say E and 1 divided by E and 2 equals epsilon R2 R1. So you see the normal component of the electric field changes inversely proportional to the ratio of permittivities. Now, this one is very, very important in our field. I will give you some examples why it is so important. Okay. We understand that by having this relationship and this relationship, I know exactly, if I know these two, how the electric field vector is going to look at this side of the interface. Please say yes. Yeah? Of course you do. For instance, epsilon R, let's take it 1, this one 2. What happens to the normal component now? Will it be larger or smaller than here? Smaller, that's inversely proportional, so we'll do half, so will be something like this. Yeah. And the tangential component will be the same, so that's this part, so it's about this. So this is what will happen. So you see you get it breaks the vector back towards the interface. That's it. But you need to be able to play with this concept. And this is a concept we use. Suppose you're a designer of high voltage constructions and you have different materials at your disposition with different permittivities. You can see, let's say, if this one is fixed, air, for instance, you can move around this vector by changing materials with different epsilons. You see that? If you would use the material with a very high epsilon, the field would go almost parallel here. Okay? If you would, well, there's no material with absolutely are smaller than 1. Yeah? If, for instance, this would have been 2, this one 4, then you go from 2 to 1, then the braking would not be in this direction, but towards the normal. Yeah? Okay? This is essential in design of high voltage constructions. Okay, you can translate that into this relation, and you can easily see that you can work with the angles here. But it's really the same story. It's all based on this one and this one. Yeah. For me, for myself, it's easier to work with this relation and this than to work with the tangent of angles. But for me, it's the same, as long as you know what happens. Okay. Now, of course, we can have more complicated interfaces. Yeah, but just something which is round. And for instance, this particular case, you can find it in the book. The right material has a permittivity which is larger than the left material. And what you should be able to do now is, if you know what equipotential lines are arriving like this here, and you know that epsilon here is larger than epsilon here, you should by now know what they will, in which direction they will break. There's one thing you should not forget. This was about field lines. This is equipotential lines. So how to do that? You know that they are perpendicular to each other. So you know that in a situation where, such as, I go back to the original one, 1, 2, where the electric field bends towards the interface, what do you think would happen with the equipotential lines? They would bend away from the interface. Yeah? Try to understand that. So if these would have been field lines there, they would have bended towards the interface. Yeah? This situation. But they are equipotential lines, so they will bend away from the interface. And that's exactly what you do in the picture. You see that? This is something you have to play with a little bit at home. If you ask me what should I do at home, really, and you can make, you can draw whatever interface you like, and you make some assumptions, and please make some sketches there. It really helps. Okay. This is not the end of this lecture. It's in fact the end of last week's lecture, but I didn't want to rush this last time, so I kept it for this week. Now we go to are there any questions right now? Please tell me. So by now we know that, okay, it's electric fields, electric fields, electric fields, and how to shape them. Yeah. But now, how to get an impression of how the electric field looks like, how to do that. Can you just calculate that analytically with all different constructions, let's say for a transformer? Yeah. How do we do that? Let's have a look. Now, we have what we call here, at least in the book, conventional methods of determining the electric field and its distribution inside the insulation. We have exact solutions, active solution for parallel plate capacitor, where the plates are infinitely long, and we have a few more, but we'll have a look at that in a moment. We have what we call the indirect method, we have separation of variables, and we have conformal mapping. Now, what is important for you to know if you're studying the book, you will see that methods 2, 3, and 4 are explained in some detail. These methods were built when we didn't have the computer power we have nowadays. So what I want you do not have to know exactly how to use these methods to calculate the field, but there are a few situations of electric fields that were calculated by these methods, which are pretty important for you to remember. This sounds maybe a bit cryptical, but when we get to that point, I will tell you. Yeah? So you don't have to know the exact details of 2, 3, and 4, how it works, but you need to know the most important results obtained using these methods. Yeah? Okay. So first, the exact solutions. The exact solutions, they all have in common that the electrostatic field between electrodes can be calculated by solving the Laplace equation. Laplace, no free charges. Yeah. And there are only 3 situations in which we can do that. One is infinitely long parallel plates. Second one is, again, infinitely long coaxial cylinders. The third one is concentric spheres. The first question that comes into mind if you think about things in practice is what benefit is this to us? Because in real life there's no such thing in high voltage as concentric spheres. At least I haven't seen it. There's no such thing as infinitely long coaxial cylinders, or what comes close? So a cable, high voltage cable. Yeah. As long as you stay away from the nth determination. Or GIS system. Infinitely long parallel plates. What can we do with that? Capacitor. So you see what's happening here. If we want to get an indication of the electric field distribution in a real component, we have to check whether we can simplify. We like simplifying things to a certain extent. Yeah? For instance, a cable, as long as we are far from the joints, maybe, or at least the terminations, we can say, okay, in that case we can use the coaxial cylinders. When I would ask you now, in which case would you be able to use concentric spheres, I guess you cannot come up with any answer. The good thing is I will suggest one to you later. But think of that.
Maybe underground cables?
Sorry?
Called concentric spheres can be think of that underground cables can represent concentric spheres. Is that possible?
Underground cables represent concentric spheres?
Concentric spheres for exact solutions method.
I tried to figure out how I can compare underground cables to concentric spheres, but maybe that's not what you mean. But
Actually, on calculating the electrostatic field, what first is that we can use like cables are also like concentric spheres.
no, that's not what. No, like concentric cylinders, not spheres. Spheres are like balls, yeah. So you have the 2 balls inside of each other, yeah. So that was a misunderstanding. Okay, but so I guess at this moment nobody knows whether it's useful or not. Okay, don't worry. Now, how to arrive at a solution for these 3 situations? I will also explain to you why it is important to be able to follow these steps, yeah? Because there's a reason for everything should work. Yeah? It should be at least. Usually there are 3 steps involved. And of course, we always use Maxwell's equations. The first step is, and here you see, can you all see, because it's a bit too much. Let me see if I can switch off this light. It's not too much. Then with the, wow. I'm sorry for that. It's nothing I can do about that. But maybe you can see there are some integral signs there all of a sudden, and no longer the differential signs. Is this strange? Well, not so, because one and the same Maxwell equation can be put in let's say, in a local and a global law, which means it can be expressed in terms of differential equations, but also integral equations. Whatever suits us best. Yeah? In this case, the integral equations are easiest to work with. Okay. The first step is calculating E from, and you see a closed integral of the flux density of the surface area, which is really Gauss's law. Yeah. So we have a closed surface, let's say the potato surface, and we integrate the normal component of the flux density across the entire surface, and then we get the charge inside. Yeah? Okay. Then we have, of course, a relation between D and E. There. Okay. And then we go to step 2. We, of course, we know the boundary conditions on the two electrodes concerning the potentials. So then we obtain the potential by integrating the electric field from one electrode to the other. And the third step is to get rid of Q. Because normally we don't know Q. Yeah? We have, okay, I can give you a cable of certain geometry, thickness, material, say potential on it, but we don't have the Q. Yeah? And so we have to get rid of the Q. How do we do that? It's not in here. I mean, this is a bit inconvenient, but I use the blackboard. Yeah? I improvise a little bit. Parallel plates. U 0. First step, you see there. We have electric field E, but I write down T here because we're working with D now. We know E is perpendicular to the electrodes. Yeah? Did I say something that you don't agree with? So, then, what? Okay, where? It's mentioned a certain charge Q. Where's the charge Q here? Where?
The surface.
On the surface of the electrodes. Yes, exactly. So let's take this one here. Q. So how should we integrate? We take this one here. Box here. Yeah? So it's three-dimensional. In fact, it's very thin because we want to stay close to the surface. Now we've captured Q in the box. Yeah? And if we integrate the normal component of D on all the surfaces of the box, then we get that. Yeah? So there are surfaces of the box that are these. So normal component of D would be in that direction. Is there a normal component of D in that direction? I don't think so. This direction? No. Inside the electrode, is there a normal component of D? Okay, now it's silent. You may assume a perfect conductor here. Does that mean there's no electric field inside? Yeah? So there's also no D inside. So there's no component of D in this direction, though the only component of D is in this direction. Yeah? Okay, so some people thinking that's good thing. So we end up with D times the surface integral times the surface, which is this disturbance times A equal Q. Yeah? Okay, well, that's nice. Thanks. Voltage equals minus integral of E dl, and you integrate from, let's say, 0 to E. This one can be expressed in a slightly different way. Epsilon A plus Q. This we can shift here. Yeah. So this one in fact says E. Sorry, it's a bit messy now, but it's Q divided by. Okay. Put that here, integrate that from 0 to D. What do you get? Yeah. Still have Q. Now we have to get rid of Q. How do we get rid of Q? Please help me. I'm a bit lost now. Yeah.
To take D times A is Q and write it in the solution U is Q divided by Epsilon.
That's one, yeah.
And to the bottom one.
So I mean, yeah. If you do that, what you suggest, you get equals D A D divided by epsilon. Okay. What you suggested? Oh, yeah, sorry.
Well, that's what I suggested.
So what did you suggest?
That's what I suggested.
Ah, that was so. Okay. Okay, there we go. Okay. D divided by epsilon A. Lose this one, you lose that one. Now we have D here. What is D? So I want to have a relation in which we have, of course, U, and then let's say the parameters that determine the capacitor. Yeah.
Maybe we can use a capacitance equals a Q over V.
Let's do that one. Yeah. Or let's say Q equals CV. Okay. And then what is C? I would suggest this. Yeah. Okay. And then you will get to the well-known expression E is finally it's V divided by D. It's a bit cumbersome, but by moving around a little bit here, finally get an expression for E. But this is just to show you that you have these three steps in general. This is too simple, really. But if we make it a bit more complicated, okay, we can create a multi-layer capacitor. Why would we do that in practice? Make it a okay, let me tell you, yeah, because I ask all these questions, I should be the one that speaks, yes? Okay. Many capacitors, if you look at them, how are they being built? They usually have aluminum foil, yeah, for the electrode. Then what you often see is a paper layer on both sides, which is impregnated with fluid, with oil. And around that, often you have let's say, a polypropylene or plastic plated. Yeah. So you have several dielectrics. So it makes sense to be able to calculate this situation as well. Okay, that's what's behind. And apart from that, let's say, even if you would have had a capacitor with just aluminum foil and one insulating material, but suppose there's a manufacturing defect, so there's a delamination, which means there's a bad connection between the electrode and the foil. So all of a sudden you have two materials. One is air, and the other one. So you want to know what is the field in the air. Because air is a weak insulator. So this is the kind of construction you need to be able to calculate if you want to know what is the effect of a delamination of a certain size. Is it dangerous or not? Will it break down or not? Okay. What you do is again you take the 3 steps. No, sun is gone, so now it's better visible. So again, we take Gauss's law. So we take the closed integral of a closed surface, of D. But now we have a number of materials, and each material has its own D. That is called still electric field, and D are in this direction, in the picture, perpendicular to your electrodes. But now we say, okay, we have D1, D2, and D3. But the only charge we have is still at the electrodes. Yeah? So what should hold true is that D1 times A is Q, and also D2 times A should be Q, and D3 times A should be Q. There's no way around that. That's the only Q. Okay, can you follow this, or I don't want to go too much in detail because I lose too much time. From that, you have the following row. You have epsilon 1, E1 is epsilon 2, E2 is epsilon 3, E3, and so on. Then again, you integrate electric field from 0 to D. You should get U again. Get an expression for U, and finally, we get an expression for the electric field in layer K. So K can be 1, 2, or 3. Yeah. So I think we have an example in store for you here. Please raise your hand. Yeah, thank you.
Why are that flux density equal to each other? I can understand it.
Why? Okay.
D1, D2.
So, that's what it all starts with, that assumption. That's not an assumption. It's a bare proof, not why. So here's the charges. If you forget about it, of course, there's minus this charge at the other. Okay, we take a closed surface. We can do it. First, we concentrate on this one here. So we take a closed surface here, and then here is D1. Yeah. For this material, maybe we have to extend it. We take this one, but we make sure that we enclose still Q. So this is D2. And for this one, we take this closed surface, in which still there is Q, we have D3. only thing that we take constant is the area here. Is that enough? So you see now that the 1 times A is this area, should be the charge inside, which is Q. But also this one, D2 times A, should also be equal to Q. And D3 times A should be equal to Q. Yeah?
Thanks.
Okay, that's it. Now, let's take a look at a practical example, and then you can relax a little bit. We walk to the lab for a nice demonstration, and then we get back again. This is real life. So we have an air gap between two, let's say, coated electrodes. So that's right there. So it can be a real situation. So we have epsilon 1, epsilon 2, and epsilon 3, where epsilon 1 and epsilon 3 are equal to the same material. Polyester coating, for instance. And now we can calculate the electric field inside the air gap by using that relation. If you do that correctly, you see that E2 equals U divided by 1 over epsilon R, and epsilon R is the epsilon of the coating of the dielectric times D1 plus D2 plus and you can approximate that by epsilon R times U divided by D. So what do we see here? We see that the electric field in the air gap is epsilon times the average field in the insulation. Yeah? So if we have a, let's say we have a polyester capacitor with the permittivity of let's say 3 relative permittivity. If we have a small air gap in this polyester capacitor, field will be 3 times larger than the average field in the polyester.
Is it something we want to have an electric field that strong in the air gap, or we try to avoid it?
And sometimes they say by putting the question you already give the answer. What do you think?
Well, I'm not sure, that's why I asked.
Anybody else? Is this something we would like to have, an air gap in the insulation?
No.
Okay, air is a weak insulator. Yeah? And on top of that, you see the field is also concentrated in the air, so it's double that. Now this is a typical example of something that can go wrong in production. Or later on in the field, if you have a capacitor that initially has perfect adhesion between the dielectric and the metal foils, but in the course of time, temperature changes, thermomechanical strain in the system, you can have delamination between layers. It's an aging process. And then such a thing can grow, and then we're in trouble. Yeah, that's the rationale behind this. That should be really clear. So that's a very good question. Yeah. No more questions about that? This is very basic, and I know for sure some of you argue and say, "Please hurry up, go faster." But it's very important that all of you understand this. Yeah, that's why I take time. So we can leave our stuff here. I will close. Do I have the key? Close the door. Where's the key? Here's the key. Yes, I will definitely close the door. We move towards the high voltage lab. Again, please don't go too slowly. Because we have plenty of things to see and to discuss. So I don't want to lose too much time getting there.